Today, we present our paper, A Hidden Stumbling Block in Generalized Category Discovery, Distracted Attention, which has been accepted to ICCV 2025. Our task is Generalized Category Discovery, GCD, also referred to as Open Set Semi-Supervised Learning. This problem was first introduced in CVPR 2022. As illustrated on the left, the green points represent labeled samples, which only contain old categories, while the red points represent unlabeled samples, which contain both old and new categories. Importantly, there is no overlap between old and new classes. The CVPR 2022 method is relatively simple. Supervised contrastive learning is applied to the labeled data, while self-supervised contrastive learning is applied to the unlabeled data. At test time, features are clustered using SSK to obtain predictions. Since then, many follow-up works have emerged. Our research builds upon SIMGCD, ICCV2023, which integrates representation learning with classifier learning and further introduces self-distillation to handle unlabeled data. This framework proved both simple and effective. In 2024, additional methods were proposed, mostly leveraging semi-supervised or unsupervised techniques to improve learning from unlabeled data. However, these approaches largely overlooked an inherent issue: problems within the images themselves. This observation motivated our central question: why does unlabeled data often lead to poorer learning performance? To investigate, we conducted visualization experiments. As shown on the left, attention maps reveal that the original Dino V1 exhibits diffuse and scattered attention. After training with SIMGCD, the model's attention on labeled data improves significantly, but the performance on unlabeled data remains unsatisfactory. We attribute this to the following. There is label guidance for labeled data, but for unlabeled data, models may rely on subtle background cues as classification shortcuts, causing attention drift. Our method directly addresses this problem. After applying our approach, the model's attention improves dramatically for both labeled and unlabeled samples. Here is our framework. After each VIT block, we introduce a time module that measures the importance of each token. These importance scores are passed to the TAP module, which prunes redundant tokens based on a threshold tau. The remaining tokens are pooled and used as the backbone's feature output. The head in our framework can be any existing GCD method. The time module computes token-wise attention through a measurer, aggregates it, and feeds it into an auxiliary classification head with cross-entropy loss to learn a vector Q, representing token importance. The TAP module averages importance scores from all time blocks and prunes tokens according to tau, which can be interpreted as the proportion of redundant information. Our approach yields particularly strong improvements on fine-grained datasets, which often contain semantically similar objects in complex backgrounds. Since our method is plug-and-play, we also integrated it into several advanced GCD algorithms and consistently observed substantial gains. On standard classification benchmarks, the improvements are smaller, which we attribute to two reasons. 1. Baseline algorithms already achieve strong performance on these datasets, and 2. Large datasets allow models to learn sufficiently well, making background interference less critical. We also compared pruning strategies across layers. Results show that averaging importance scores across all layers before pruning significantly outperforms pruning at individual layers, underscoring the importance of multi-scale pruning. Additionally, we introduced a small training trick. Since the baseline uses 2 augmented views, we apply pruning to only one view while keeping the other intact. This preserves information completeness and, at the same time, serves as a form of data augmentation. Empirically, this single-view pruning strategy delivers higher performance. That concludes our presentation. Thank you for your attention.